Welcome everybody. Today is the last day of class before Thanksgiving, right? So happy Thanksgiving. I hope you get to say that to lots of people and that we all have a little bit of respite if possible. Today we're going to cover failure criteria, and we'll resume our discussion on failure criteria when we come back on Tuesday. As a reminder, there are a number of things happening before the semester ends, but not too many in this class, actually. Let me see if I can pull this up. All right, great. So you can see that we are here, failure criteria 1. So we only get to meet 1, 2, 3. No, this is wrong. We are here, failure criteria 1. This is the old syllabus, I'm sorry. So everything's just been shifted 1 down. I've opened the wrong file. So we are here-ish, okay, if that makes sense. And then we won't have the buffer. That'll be session 25, 24, and 23. Okay. So we're rapidly coming to the end. And if you have questions, please come and see me during office hours. Please go and see Proj during office hours. If you haven't done the lab yet, please make sure you get it in. Okay, and then yeah, we'll have our final class reunion on the 17th of December. Except it'll be sad because we have to be in 2 classrooms, I guess. So, but that'll be the final thing. All right. Any questions about how things are set up? Okay. Thank you for being here, and as we discussed in class, I understand that people have plans and things. So if I completely respect your actually that didn't work. So if you need to attend to other things, here's the attendance. And for those online, you should be able to, I think it should be visible online as well. So this way, everybody can be on their merry ways if they want to be. Okay, so let's, oh, okay, we're still going. All good? All good? Okay, all right. So let's go on our merry way. We are going to talk again about material testing and ductility. We will talk about maximum normal stress for brittle materials, and we'll talk about maximum shear stress for ductile materials. Finally, after I've said it I don't know how many times, we begin to formalize what it means for materials to yield or fail, and we are able to get a handle on all the different techniques and tools that we have for describing stresses and strains to be able to mate or match these values, these parameters to criteria. And ultimately, as either a design engineer or even a consultant or someone who does analysis, it's very important to understand why or how or if or when the materials that you're using in your particular structures that you're designing would fail. And yes, there are some people who are just fascinated with the material itself, and they want to design new materials, they want to engineer new materials, and we have a whole department for that. Okay, it's wonderful. And there are others who are more interested in designing structures and based on the properties of the materials that they buy off the shelf. And then there's some people who are doing a combination of both. They do a little bit of manipulating materials, and they do a little bit of figuring out how to incorporate them into structures. So you could be, and then there are some people who try to do this many, many, many times. So manufacturing, right? These are all valuable aspects of engineering, and depending on where your interests lie, you might be more fascinated with the material aspects. You might be more fascinated with the design aspects. You might be more, fascinated with prototyping. You might be more fascinated with manufacturing. And they're all especially important in today's age, especially as manufacturing is a top topic, geopolitically, shall we say, and economically. So once you have the material, right? So if you're a mechanical engineer at Rutgers, you'll take the Mech Props class, which is taught by material science. If you're an aerospace engineer, we don't have it. We got enough other stuff to handle, I guess you could say. Nonetheless, for our intents and purposes, we want to understand the tensile and compressive tests. And you've done tensile testing now. Most of you have done tensile testing because we're nearing the end of the semester and we have had a lab that describes tensile testing. And we didn't do compressive testing in that lab. It would be nice to have more time, but anyway, we did what we could. The general purpose is to characterize the properties of the materials such that we can figure out how they'll behave when we form them or when we incorporate them into structures. That's the basic idea. And we've talked about this previously, right? You're not going to take the Eiffel Tower and put it in a tensile testing machine. It's just not practical. Okay? It would be probably phenomenal to watch, but also phenomenally expensive. Okay? That said, there is validity to putting the whole system together and seeing if it will work, right? We're seeing that if that can be done quickly, and if you can fail fast in aerospace, right, without risking human lives, and you do the cost analysis, or you have the big contracts, whatever it might be, okay, you can move quickly that way too, right? So there are different philosophies in terms of, okay, which level are you going to engineer and engineer so that you don't have to worry about it. When systems no longer are simple, right? We understand if we want to try to keep it simple, silly, that if as soon as you can't do that, then sometimes you have to do extensive testing, and there's going to be some destruction and failures, and then you learn and you move on. So for the tensile testing that we do, we relate the average normal stress to the average normal strain, and we are typically applying a constant rate of strain while measuring stress. Okay, so now these words probably make more sense than they did the first time they were flashed on the screen. Okay, so I probably said it prior, but most tensile testing machines, they control the rate of displacement, okay, and then you can calculate a strain rate, okay, with that. Why? Because displacement over the initial length, right? That gives you the strain. So the displacement rate would be length per second, right? So how much am I moving the head up of the tensile testing machine per second? The strain rate is just that displacement divided by the initial length of the sample divided by that time. Okay, so you'll often hear people talk about strain rates, and we usually try to go for lower strain rates, except if you're doing something that involves high rates of failure. And you can think of systems, where you would be very interested in being able to characterize the effects of, say, impact or something that's moving very quickly as it hits the material. Okay, so for our intents and purposes, the yield strengths that you're seeing have been done at modest speeds. With the stress strain measurements, you've seen this before. We use the original cross-sectional area for what we call engineering stress, and we use the original length, the gauge length, okay, to calculate what we call engineering strain. And we've also discussed that if you have a softish material with a lot of Poisson ratio, you could have a situation where you're going to have the cross-sectional area changing. And so in those scenarios, as the cross-sectional area changes, you might be interested in calculating out what the true stress in that material is, right? So you got to figure out some way to figure out, okay, what's the cross-sectional area, what's the force in real time or in post-time to be able to figure out what the true stress is. Yeah. So, and strain also can be described in different terms. We've done this before, the stress-strain curve, and we see, okay, there's a proportional limit, right? So that's where you have a nice elastic modulus. That's the slope of the stress versus the strain. And then it can go a little bit further up to the elastic limit. So maybe it's no longer perfectly linear with the slope, but it gets into this little regime where it starts to just kind of turn the corner, but it doesn't essentially start yielding, and you can go back down. Okay, and then you get to the yield strength, the yield limit. All right, where you really are going to start to engage plasticity, and then you hit an ultimate strength, and you hit a fracture limit at the end. And yes, we've talked about fracture a little bit in the past, and I've said, hey, look, fracture really is about cracks propagating. Even in these types of systems, okay, what you're going to have is some type of crack that's going to form in a ductile material, at least. And then when that crack opens up, gets a little bit larger, pop, goes the material. Okay. So we have the ability, we talked about modulus of resilience, we talked about modulus of toughness, right? These are other material parameters that we're going to be discussing. Today and tomorrow, or Tuesday, okay, tomorrow, hopefully you're not thinking too much about mechanics and materials, okay? But if you are, go ahead, do your homeworks, that's great, enjoy, take a nice leisurely pace. I hope you have a good holiday. We're mostly interested in what is the yield strength. Okay? We don't want to design for this area. Why? Well, you're going to have some elongation of your material. Okay? You're going to potentially have some variability that contributes to hitting fracture, which you don't want to do. And the material doesn't go back elastically. So if it's cycling and it's loading, right, it's not going to go back to zero if it were to do that. But even if it's like the Statue of Liberty or something like that, where it's just got a constant load on it, it's you don't want to be out here. You could have things like creep, okay, which we don't talk about in this class, but I guess we're talking about qualitatively, in that as you have a significant load on the material, it bubble gum or something like that, and it keeps going, even though the force is not increasing, right? And that's kind of the definition of what's happening here, right? Force is not really increasing that much in this region. It's because the slope is kind of flattish, right? And so when that happens, right, you could get elongation, and if you keep getting elongation, the cross-sectional keeps going down, right? Eventually you're going to get into fracture. So for many reasons, we design for the elastic regime. Okay. That said, I was at this conference and very clever, and so we've done some work in kind of flexible electronics, wearable electronics, things of this nature, and I was like, oh, sometimes you see a great idea that comes out, and you're like, I should have thought of this. I mean, I wouldn't have really necessarily implemented it, but what the researcher was presenting was, look, we make sensors to go on people. Okay, that's what wearable sensors are supposed to be. And in the future, we want them to be, even more complex than a watch, right? We want to be able to monitor sweat, and they're already doing that. Some people are for performance and things of that nature. But they presented this idea. Imagine you put a sensor that's very much tied to an organ or something in the body, like an internal sensor. Well, that organ is going to grow. And if it grows and your sensor doesn't grow with it, that's going to cause a problem. Right? You got to change the sensor or something of that nature. Now, yes, many of these sensors that we work on are somewhat disposable. But this was a good thought experiment. Imagine that we designed our materials to expand with the organs or the tissues or the body parts. It's like, they showed this picture of, the baby becoming an adult and then shrinking as they got older again, right? So they were talking about a viscoelastic sensor. So yeah, we have stretchy materials that go back and forth, but there could be a case where you want something that's like bubble gum, where it actually stretches with the individual as they grow. I was like, wow, that's a pretty cool idea. I wish I thought of that. So anyway, so there could be a case where you do purposely design for that regime where you're yielding the material. We've talked about yield strengths in the past, and here are a number of examples of different yield strengths. And for the steels, we've also talked about how the different, and we haven't talked in detail about the heat treatments and the different ways to add plasticity. But we have discussed that, yes, you can have quite a bit of range in the yield strength of a steel, even though its elastic modulus stays the same. And this reminds me of another anecdote. So someone was talking at church about life and going through hard problems. And they have some background in material science, and I didn't necessarily see it coming, but they're like, we actually, in order to get through life's problems, in order to become stronger, okay, we actually have to be deformed. We have to be plastically manipulated in some cases, right? We have to be, we go past our yield strength. It's like, wow, there's a great analogy for life, okay? So you can think about that, right? And we've talked about that, right? We've talked about strain hardening in this class, and how if you go beyond the elastic limit, or you go beyond the yield strength of the material, right? And you go up that, it does go up a little bit, right? In the stress strain curve, you have to, as you unload, right? You can go back down to zero. There's going to be some residual strain, but now the yield strength has increased to whatever level you got up to. Okay, so anyway, another kind of fun life lesson, maybe, that comes from thinking about the yield strengths of materials. And also you can use heat, and you can use annealing. And so for those of you who get to take Mech Props, you'll learn lots about these different concepts. And how grains grow, and how actually you get strength from what are called dislocations. So you actually introduce imperfections. So another analogy to life, right? As we make mistakes, we learn lessons, but there are a bunch of imperfections that have been incorporated into our lives. And the same thing is for these ferrous materials. Okay. So, ductility, we've talked about this a little bit before. This is the degree to which a material can sustain plastic deformation under tensile stress before failure. And it also describes the ability of a material to absorb or shock or energy. All right, so we can talk about modulus of resilience, and we've talked about different ways to report ductility. And I don't think I've really had an exam question where I said, hey, this is the percent elongation, this is the percent reduction of area. Can you kind of give me a perspective on how ductile is this material more ductile than this other material? Haven't really done that in an exam, but it's good to know. And it's also good to know what brittle failure looks like. So one example of brittle failure is chalk. Okay? So if, yes, if I stuck this in a nice tensile testing machine, what would we be expecting when we look at the surface that it creates? We expect, well, what do you expect? Look at the pictures, right? What do you expect? If I were to put this in a tensile machine and take it to failure, what do you expect to see? Yes, Mark?
Brittle failure.
Okay, yeah, brittle failure. And what like literally, what am I going to see? Yeah, it should be kind of straight across, right? And maybe a little bit of a little jumpiness, right? Any necking? No, right? So you're not going to see the material kind of go into a nice hourglass shape before it fails, okay? So what's another way? If you had to choose how to break this in your hands, what's the way you're going to do it? Yes? Go ahead. Just snap it, right? Yeah, just snap it. Okay, and what types of stresses am I inducing on this brittle material if I snap it? What type of loading is that? The snap action. Yes?
Bending.
That's bending, right? So we've done bending, right? So I can get, and so part of it's going to go in compression and parts of it are going to go in tension, right? We now know this, right? There's going to be a longitudinal axis, right? And we have a neutral axis where you're going to have compression. Well, if I do it like this, right, it'll be compression in the bottom and tension in the top, right? So let's do an experiment, right? If I do this now, what kind of surface should I get? This is brittle material. I have normal stresses involved with this bending procedure, and that's pretty good, okay? All right, so you see that this is now, kind of jagged like we were expecting, and I was, you can pass it around as well. Here, now you guys, you can keep breaking it, I guess, if you want. Okay, but there's going to be more chalk. Don't worry, there's going to be more chalk coming up for you. Okay, so that's an example of brittle failure. All right, you can break it, you can crumble. I got a little bit more chalk here. Okay. At the end of one semester, one student gave me this enormous chalk. Like, the diameter's like 1.5 inches. Essentially was, I dare you to try to break this for your next class. I think I can snap it, but I can't. I'll show you something in a few minutes that's kind of cool. I have trouble with breaking it in other ways. Okay, so this is kind of a stress-strain curve for a brittle material, and it doesn't have much of a ductile region as it doesn't really have much of a yield. Even this kind of turning over kind of behavior, right? Flattening behavior on the curve is maybe misleading, okay? But it just kind of catastrophically breaks. And as we've discussed before, the compressive strength is typically higher than the yield strength, than the tension. Okay? And then you can see this cool little, I'm sorry, you can't see. You can see this cool little video where you have this snapping, or essentially, catastrophic brittle shattering of the material. Okay? Now, there are multiple theories for failure. There's not a single unifying theory for failure. Okay, and I mean we're just talking about essentially. Let's see. Here's a laser pointer. Finally, okay. We're talking about even at this point we're kind of just breaking the whole world into ductile and brittle materials. Okay, actually we're not, because we're going to say this is brittle, this is ductile, and if it's something in between, we're probably going to say use your judgment. Okay, but yeah, people study all kinds of failure. My first undergraduate research project was working with this now deceased, but an emeritus professor at the time who was an expert in cracks. Okay? And so we were looking at some other students had written some MATLAB code, and he had what were these ideas and concepts for what are called slipline fracture mechanics. And so we were not doing finite element like you've done here. but we were looking at how the crack opened up and what the surfaces look like and getting the right shapes, just like in a MATLAB script, right? So kind of using some mechanics. Okay, so it was using numerical simulation, but it was really just running, and it's not just, it was complex, but running a simulation based off of mechanics, like what we discuss in this course, plus a whole field of fracture mechanics. So, and actually, cracks are very hard to model accurately with finite element. Why would that be? Well, finite element, right, means that the elements all have a particular size. And fracture, right, a crack is a very, very, very small fissure, essentially, in the material. So it's going to be very hard to discretize a material or a structure sufficiently to make sure that you get the correct idea of fracture. Now, there are different techniques out there, okay, but fracture is a hard problem. Haha, hard. All right, and so in this case, he was an expert in slip-line fracture mechanics, and he was working to better understand how to ensure that nuclear waste facilities did not develop cracks and would not have to be repaired. Okay, so yeah, we're not going to account for a bunch of different factors, and we're even going to say that the criteria that we discuss, there are two for brittle materials. Today we discussed maximum normal stress. On Tuesday we'll discuss more failure criterion. They should be used with caution. Okay? And you have this kind of idea already. You see something shatter, it's sudden, it's catastrophic. And if there are different defects, if there are different micro cracks in the structure, in the material, that can lead to very different results. Okay, so the brittle materials, we have criteria, but we should be careful with them. So there is much variability, and the resulting behavior can be sudden or catastrophic, and even shattering. Okay, so that's your example of brittle materials. Nonetheless, we can write very clean, nice exam questions that say, does this fail by maximum normal stress criteria, right? So it doesn't exclude us from that. Now, the ductile materials, we're going to discuss two different failure criteria. And one criterion is the maximum shear stress theory that we will discuss some today. And Tresca is the name that you will hear associated with this. You can even go into your finite element packages and it will spit out Tresca stress, the Tresca equivalent. Okay, so that is essentially telling us what the maximum shear stress is at all those different elements. And then the maximum distortion energy, we'll talk about that next time. That will have the name Henke or von Mises. And so if any of you have done some finite element analysis besides what's done in this class, you'll have probably seen that von Mises is a very common way of describing the equivalent stress that a material might be experiencing. That von Mises stress is essentially an equivalent stress that allows us to compare directly to the yield strength of the material. That's one of the reasons why it's so popular. Okay? Remember, we had to do a little bit of acrobatics when we think about shear stress and how it relates to yield strength. Okay? We can think about the Mohr circle. We can talk about this a little bit, but that's uniaxial loading, right? So that the radius of the Mohr circle for maximum shear stress and uniaxial loading, right? The radius is going to be what, and we're talking 3D, right? Because you have a sigma 1 and sigma 2 and sigma 3. So you have sigma 1 of a significant value under uniaxial loading. Okay? Remember uniaxial loading, that's the tensile test. All right? So there's a sigma 1, and then what? Sigma 2 and sigma 3 are 0, right? Yeah, they're just 0 because I'm stretching in one direction and I'm not stretching in the other directions. Okay. So since sigma 2 and sigma 3, here, let me just right? So what I'm talking about in uniaxial loading, right? What we have is a material being stretched like this. And so we can say this is sigma 1, and sigma 2 equals sigma 3 equals 0, right? So then, if I draw the Mohr circle, okay, you tell me, what does Mohr's circle look like? Anyone? I'm saying I'm selecting a material element. Does this help in here? A material element right there. Okay? And this could be the x direction. This could be the y direction. Okay? Okay? And now I'm saying that sigma 1 sigma x is essentially equal to this sigma 1 that I'm applying. Okay, so first off, what have I described? What state of stress are we in this case? If I'm saying I have a sigma x, and I have sigma, so I have a sigma x equals something, I have a sigma 2 equal to, or a sigma y equal to 0, and a sigma z equal to 0. So what state of stress will that be? As a name. Is it maximum in-plane shear stress? Is it a state of principal stresses? Yes.
Principal stresses?
Yes, it's state of principal stresses. Yes, okay. So now I've got a sigma 1, a sigma 2, and a sigma 3, right? No shear stress.
Yeah.
At least the way I've described it at this point. Okay, so then tell me, how do I draw a Mohr circle?
So you want to get the average.
Yes.
So basically, x was a sigma x plus sigma y over 2.
Yes.
Center. And
Yes.
for the radius, it's basically sigma x, or the square root of sigma x minus sigma
Okay.
average is squared. And that'll be your radius.
Okay, so you're telling me I have a sigma average, right?
Yeah.
And what is that equal to?
Basically, sigma x plus sigma y over 2.
Yeah, and then simplify. Half of sigma x or half of sigma 1, right? The way I've described it. So it's just sigma 1 over 2, right? Okay? Now, what should I do next, probably? So I've got the center.
You want to get the radius. So you basically want to just do, since there's no shear stretch, that's 0. So it's basically square root of.
No, I don't want that. Before I do that, just geometry.
Oh,
No, you're good. You're good. You could do it that way.
all right.
But what should I draw? Tell me what to draw.
You want to draw the.
No, you're doing great. I'm putting you on the spot. Or you're putting yourself on the spot, actually. Yeah, because you've raised your hand. But good, yes.
You want to draw the adjacent
No, before I do any triangles, there's not really a triangle to be drawn here. What do I draw?
the circle.
Okay, but but I have a center.
You want to draw a circle with this center being the average.
Okay, but I've got an average. I need a radius. So we're going back and forth here, I think. What should I draw at this point? Yes.
The principal stress.
Yes, okay, so tell me specifically.
Sigma 1, 0.
Okay, yeah, so right, and where is that? Yeah, and specifically it is going to be twice, right? That's it, right? So this is now the sigma 1. Okay, so that's 1. What else do I draw? I need another, well, I actually don't need another dot, but I might as well put them on because it'll help me out. Yes, right? Sigma 2, sigma 3 are equal to 0, right? So I can go ahead and I can draw those right there. This was what the exam was on last week, right? Yeah. Oh my goodness. I think you're just being kind to me, making me, yes. All right, so now, right, so to your point, how do I draw the circle now?
Basically, the center is going to be the average, and you got to go through sigma 1 and sigma 2.
Right, yeah, okay, so that's my crummy looking circle. Okay, now what is the radius? No triangles, no square root of nothing. What is the radius?
Basically, what is it? Sigma 1 minus the average.
That's right. And what is that?
Sigma 1 minus, basically, Sigma 1 minus the average. Sigma 1 over 2.
Yeah, you got it, right?
Yeah.
No complex math, right? Just good old secondary school geometry, all right? So this is sigma, the radius, right, is sigma 1 over 2. Okay, now what is the absolute maximum shear stress? This should be rapid fire. Hold on. Yeah, so what's the absolute maximum shear stress? Or let's say, what's the maximum in-plane shear stress? Yes. Yeah, it's sigma 1 over 2. How did you calculate that? This is the radius, right? So it's the radius here, right? This is where the shear stress is going to be maximum, right? At either the bottom or the top. I mean, the top is just negative of it, okay? Because it's a circle, right? So the absolute maximum shear stress is here. Tau max. I know. I should have maybe. I didn't expect to spend that much time on this, right? So this is a very important. This is maybe the most important Mohr circle that you will cover in this class. Why? Because we test materials under uniaxial loading. Okay? And if it's a ductile material, what I've just said, or what we've just said, is that they fail because of maximum shear stress. Okay? So we're testing materials like this, but they fail because of this. And the Mohr circle, this is the fastest way to get there. Or you just remember, it's going to be whatever the yield strength is divided by 2. Why did I say that? Why did I say the yield? So you just said sigma 1 over 2, right? Why did I say yield strength divided by 2? Now? Yes.
Okay. Well, the yield strength is how the material would fail if you're doing it like this way, but we know it fails half of that in shear.
Right. Right. So the maximum load, remember we have the linear elastic, perfectly plastic models, right? And remember that we only care about the elastic regime. And we're, for our intents and purposes, saying that the elastic limit and the proportional limit and the yield strength, they're all the same, right? We're not going to get into too much detail there, okay, the difference of these three. So the maximum stress that the material can handle under uniaxial loading, and again, uni means one, axis means, I don't know, axis? I don't know, axos or something, right, in the Greek, or the Latin, sorry. You have one direction, right? Right? The band is playing one direction, and yes, there's been a recent loss, so that's sad. Nonetheless, right? The band is playing, and you're listening to, like, you don't know you're beautiful or something, right? And you're listening to it while you're doing the tensile test in one direction, okay? And you can only hit the yield strength. That's the maximum you can put in that one direction. Okay, why? Because that's when the material starts to yield, and we don't want that to happen in our real life, right? So we need to figure out what the equivalent, if it's a ductile material, we need to figure out what the equivalent shear stress is. And so this sigma 1, that's the maximum load, that becomes the yield strength. So now we actually are kind of thinking about a radius expanding, okay, on the Mohr circle, and we expand it all the way out to the yield strength. Okay, and then we see that the absolute maximum shear stress is going to be that yield strength divided by 2. And I'll have some more slides on this in a minute. Okay, but since we were on this, I thought we just discuss it quickly. Now, if it's a brittle material, then we care about the maximum normal stress. So then we just care about SY. Okay, then we just care about the yield strength. All right, so that's uniaxial loading, but that's indicative, okay, because the maximum normal stress is out here, where we have our sigma 1. Okay, so the Mohr circle is extremely useful for quickly being able to remember what in the world is happening in uniaxial loading and what is the equivalent state of maximum shear stress. Why did I say absolute maximum shear stress, and why am I being casual with saying like it's not just the max in-plane shear stress? Well, there are all three of our principal stresses on this diagram. All three of them are there, right? We have sigma 1, we have sigma 2, and sigma 3 right here at 0. Okay? And so I could go through the exercise of drawing the 1-2 circle, the 1-3 circle, which I actually have, right? And then there's going to be another circle would be like the 2-3 circle. But that's just a dot. So it doesn't appear on the Mohr circle, right? So this is a case where the maximum in-plane shear stress that we're used to drawing, or we learned to draw first, is the same, gives us the same result as the absolute maximum shear stress. Okay? Any questions, conversations, philosophical ideas you'd like to share? Yes, no, yes, no, okay. All right, so let's move on. Well, actually, we'll just move on. There's a few things here on this slide that I didn't talk about. Ductile materials also have less variability, and the failure is gradual, and there is this necking behavior. Okay. So one of the questions on the homework is to figure out or to just sort these materials into the brittle and ductile categories. Now, these may not be completely hard and fast rules. Like if you Google, is high carbon steel brittle? You're going to find some website that says no. Okay. Typically, yes. All right? Higher carbon steels are typically going to be in the brittle category. How do you get carbon into a material, by the way? Anyone know? So we're talking about like percent carbon. Like how do you get it in? Yes? Okay, so for some of the polymers, you could think about bubbling gases, and maybe they do that for some steel processing. That's not the typical manufacturing process of doing. I mean, I'm sure you could. I'm sure it would if you change the environment, okay, in which you have heating going on, right? So if it isn't a carbon dioxide environment and you get it really, really hot, then yes, you could imagine that there's going to be some diffusion into the material. Okay, so okay, sure, valid. Not a typical manufacturing process, but sure. Okay. Other ways? Any ideas how you change the carbon content of steel? Well, it involves heat. So I think we're on that area, right? So essentially, you can take, it's called coke, all right, or graphite, all right. So coke is a product of essentially making something like charcoal, okay, which comes from petroleum or charcoal, okay. And so then you kind of heat them up, or you heat up the metal, and then you can kind of crunch the coke into that material, and that's a way to change the carbon content. They're like, you can kind of like cast them and squish it in. There are different ways to kind of doing this, but it involves heat and essentially mixing in some type of charcoal-like material. Okay? And that's how they change the carbon content. Do you think gold is a brittle or a ductile material? Huh? You think brittle? Interesting. So if I were to take this and I were to kind of like start to play with it with like a wrench, not a wrench, pliers. I'm not going to do that for various reasons, right? Do you think it's going to catastrophically shatter? No, this is an example of a ductile material, okay? Maybe, yeah, and then what about What about epoxy? Anyone used epoxy recently? No? Are the RFR people all gone? No one from RFR that's doing thermoset or the layups, the epoxy layups? Okay. Epoxy is typically pretty brittle, okay? And it's a two-part material. When it hardens, it's not going to typically does not allow you to kind of nicely get it to deform. Okay, nicely, that's not even good. It's brittle; it will shatter. Okay. Anyone ever has anyone used epoxy for anything? No. Okay. Well, if I had to choose a material that you would start to play with in a lab here at Rutgers, my choice would be silicone, actually. This material will change your life. It changed my life. It's transparent. It's a rubbery material. It can actually take reasonably high temperatures for a polymer, 200, 300 degrees Celsius. And what's cool about it is you can get it in two parts. That's typical for thermosets, and you mix them together, and then you can pour it into whatever you like, and it will has a very low surface energy, and it will essentially wick and get into every single crack as possible. Okay, so this material is used for micro and nano replication, so it can replicate features in a surface. So, say you had some type of semiconductor process, or not even semiconductor process. You just had a surface that's shattered, whatever it is. It will replicate that detail very, very intimately, down to a couple of nanometers, or 22 nanometers, something like that. Okay, so it gets into, because of its low surface energy, it gets into every nook and cranny, and it can also come in pretty low viscosity, still higher viscosity than water, typically, but silicones, as you know, they have a lot of different viscosities. All right, so this material, it can change your life. All right, as many materials can. Okay, let's talk about the brittle materials and their failure criterion here. Okay, so we're talking about maximum normal stresses, and you're going to see these types of plots, and they'll make more sense in a few. Well, this one will make more sense today, this one will make more sense in a little bit. But this is actually for. Okay, this is just the opening slide, all right? But this is, okay, so just so you know, this one here, this is for brittle materials. This one here is for ductile materials, right? So I didn't delete this one here, but this is the type of diagram we're going to be talking about right now. Okay, so once again, failure is due to fracture, and there's not really much of a warning. It just goes, okay? So, dropping a glass, I don't know, we seem to introduce our kids to regular ceramic plates and cups early on in their lives. And when we go places and stay in an Airbnb or something, we typically break dishes. And we have to often send messages to whoever the host is and say, sorry, we broke your thing. And sometimes they're nice, and sometimes they say, pay us some money, right? And at home, it's very common for us to break dishes. They're not expensive. It's not like expensive china. They just break, all right? And yeah, there's no warning. It's sudden, and I'm learning to not get too upset about it when it happens. Here, right, the fracture surface that you expect is going to, end up yielding something like this when we apply some type of normal stress. And here, once again, is the Mohr circle, and we get to the sigma max. And now, For torsion, we have a helical surface of fracture, which is insensitive to compressive stress. What are we talking about? Okay, so let's think about this for a second. Here, right, we took a piece of chalk and we broke it using normal stress, right? And that kind of, that's kind of to this first point, and we saw these nice kind of rigid fracture surfaces. And now let's think about what happens in torsion. Okay? So here is a material element. It's undergoing a material element on a rod or a shaft, and right, you agree this is what the state of stress would look like under torsion, right? And what is that tau xy here? What is its magnitude? How do I calculate that shear stress? It reminds us of a certain university or certain college in New Jersey. Yes, you're doing the symbol, right? So it's torque times the radius c divided by j, right? The polar moment of area. Okay, so Tc and j. Okay, so we have tau xy, right? So we don't care too much. I mean, we can write it out. I didn't write it out, Tc over j, right? But that's what the shear stress is. And then this is the Mohr circle. Does that make sense? How did I do that? What was the sigma average here? Up in the top. I don't know your name. What's your name?
Joseph.
Joseph?
Joseph.
Joseph. Okay, so what's the sigma average here?
Basically, sigma 1 over 2.
Oh, okay, all right, fine. What are sigma 1 and sigma 2 here?
Let's say sigma 1 is going up.
No. What's its magnitude? This is a coordinate system. If I'm in pure torsion, if I'm in pure shear,
Oh, it's just 0.
this is 0, right? Yes, right? Okay, so where am I on the Mohr
You're at
circle?
the center.
Okay, so that's where the center of the Mohr circle is at 0, right? What state of stress? How would I describe the state of stress on this Mohr circle? So I've drawn a circle. It's centered there. Okay, what is the shear stress? Or I kind of said it. Where am I on Mohr circle for this state of stress? Right, because Mohr circle, you move around the circle, right? So where am I?
Max shear stress.
Yes. Okay, so I'm here.
Or the top.
Yes, so I've got essentially like a line going across. Okay, but I'd be like down here, right? Because that's where I have my tau max, and that's where I have 0 normal stress. Okay, so I'm there. Now, how does this material fail? It fails not because of the maximum shear stress. It fails because of the maximum normal stress. Okay? So if I were to draw another element, okay, like this, which is now a 90-degree rotation on Mohr circle, but a 45-degree rotation of the actual material element, what would the state of stress look like? It would look like this. I'd have, right now, one stress coming out in the x prime direction. That's going to be in tension because it's out here. And the y prime direction, right, it'd be this compressive stress like that. Everyone see this? Okay. So that means if the normal stress is causing the failure, you can think now this element is going to fracture, okay, along this normal stress. All right, you see this? So if this were the x prime direction, if this is in tension, this is the y prime direction, whatever. If I flip it, however I look at it, if I've got tension in this direction and compression in this direction, do you see that it's going to break like this? Or it's going to break, coming back here, it's going to break along this line? When I say this, it would break along that line. Can you see that? That's the normal stress causing it to pull apart. So, now, if I have torsion, and I know I break a brittle material because of normal stress, what is the fracture surface going to look like? Well, we already did the normal stress, right? We know that was clean break down the middle. Okay, but if I twist, what's it going to look like? Yes?
Say center cross-section area a little more narrow, it's twisting.
Yeah, so it's okay, so it's twisting. And let's say also, you see there's a 45, something strange is happening at 45 degrees, right? It's going to want to break apart at 40 with a 45 degree, at the 45 degree angle line. So the answer is actually here. You have a helical surface of fracture. It's going to be helical, and that's going to be at 45 degrees relative to the orthogonal, this direction. Okay? So let's see what happens. I'm going to twist, okay? Look at it. Oh, that's not a real good one. Okay, but it's not a bad one because the stuff is all over the floor. Okay, that's actually pretty good in the end. Okay, do you see this? Well, I'm showing the camera, right? But you see, like, there's this, like, helical pattern, okay? That's because that's a surface, that's a fracture surface that had the maximum normal stress on it, okay? So you all, some of you, I don't have chalk for everybody, but if you like, okay, you can take a look and take some, you take a piece. I don't have enough for everyone, but we're a smaller class. I could have brought, if I had known, well, anyway, hopefully you'll get a chance. There's some over, oh yeah, I got tons. Never mind. Okay, so pass it around, okay? Pass it around. The next person might be upset with me, actually. But we'll leave them a bunch of pieces, okay? So you should be able to see this. If you twist it, you should be able to see the helical structure form. Okay. All right. And see, that's just kind of what I've drawn here. So, what is the criterion, though? That's nice. Okay, the criterion for this maximum normal stress, it's typically good for situations where the ultimate strengths in compression and tension are close to each other. Okay, we'll talk about how to handle that when they are not. That's the Moore criterion coming up next time. It's kind of, in some respects, it's a little bit simple. You're just kind of looking at a Moore circle where you've got, this maximum sigma 1 or sigma 2, it could be in compression or tension. And we want to make sure, okay, like if you go above a certain limit, the ultimate, strength of the material in compression or tension, so sigma ultimate, this is like the new SY, all right? Because another thing that happens is when you deal with these when you deal with these brittle materials, you typically are thinking more about the ultimate strength instead of the yield strength. Because do they yield? Not really. They just fracture. Okay? They just fracture and crack. Okay? So that is often called the ultimate compression, ultimate compressive. So I'll just put a little note here. We often think of this as an ultimate strength. And it's just a rapid fire. So in order to be safe, the Moore circle is going to be essentially between these goalposts, where these goalposts are these verticals. So I like to think of maximum normal stress theory as kicking field goals. All right, if you kick a field goal, if you're between the goalposts, you're probably going to be safe. If you go wide left or wide right, not so good. All right, you're going to lose. You're going to fail. Okay. Now, what does that look like on a different type of plot? Okay. So what is this? This is called a sigma 1, sigma 2 plot. The sigma 1, so we're going to be thinking now. So, you know, the Mohr circle is a sigma, which is all the normal stresses, plotted against tau. In this case, what we're thinking about is sigma 1 plotted against sigma 2, or sigma 2 versus sigma 1, I guess. You know, that's how you're supposed to say it. Okay, and what is going on here? All right, if you look at it, right, you could have a Mohr circle where sigma 1 and sigma 2 are the same, and they're right here at this point, at the ultimate. So let's say sigma 1 equals sigma 2 equals sigma ultimate. What does that Mohr circle look like? A dot. Okay, the Mohr circle looks like a dot. Where is that point? Right here. Okay. So if your Mohr circle is right here, you're right on the cusp of failure. Okay. If you have sigma 1 equals sigma 2, or sigma 1 equals negative sigma 2, so at this point or at this point, then you've drawn a Mohr circle that looks like this, the one that's shown here. Okay? And we're assuming essentially that sigma 3 is equal to 0 here. Okay? But it could be equal to something less than sigma 1 and sigma 2 for maximum normal stress theory, because we only care about what the maximum normal stress is. How do you calculate what the maximum normal stress is? You have to use the principal stress, or you have to think about getting into a state of principal stresses. Okay? That's how you're, right? Because if I give you a state of stress where you have some shear stress and you have a sigma x and a sigma y, right? So you have a sigma 1, a sigma x, sigma y, tau xy. You're going to want to get to sigma 1 and sigma 2 and sigma 3 to do this criterion checking. Does that make sense? Right? Because I could be at this location, right? Which is an equivalent state of stress, or maybe better said, I could be at this location, for example, okay, which is an equivalent state of stress to this location right here, right? It's just a different orientation. And if I need to calculate a safety factor, I better not use this. What is a safety factor? That's right, how much buffer. We'll talk about safety factors next time. But it's how, you know, how much you can multiply the load, essentially, and then hit failure. Okay. So you want to be able to think about going between these Mohr circles and these sigma 1, sigma 2 plots. Anything in here, right? So if I have sigma ultimate, you know, or let's just do this one right here. This is just sigma ultimate comma 0, right? That's kind of a nice one. That means that I have sigma 1 equals sigma ultimate, sigma 2 is equal to 0. That would kind of describe this situation, this Mohr circle right here, that one, right? And that would be, you know, on the brink of failure. If I have sigma 1 equal to half of sigma ultimate, right, I'd have a safety factor of 2, and I'd be having a Mohr circle that's kind of drawn in here like this. Okay. Any questions on this? About how you go between the sigma 1, sigma 2 plot and the Mohr circle? Which one do you want to think about? Oh yeah, we had a question? Yeah? No, okay. So what do you want to, you're going to see, you might be asked to draw a sigma 1, sigma 2 plot. Okay? Again, on the Mohr circle, you're just trying to kick field goals. So any Mohr circle that you can draw between these goalposts, you're good. Anything outside them, bad. Well, I shouldn't say bad. Okay. When you write scientifically, you're not supposed to say good and bad. That's too subjective. We'll just say we exceed the limits of the material, right? Or we're within the yielding limits of the material. And the same thing here. If you're outside the sigma 1, the box, then you're going to have failure. Okay, so here we have a brittle material, okay, that has this state of stress. Sigma 1 is equal to 50 megapascals. Sigma 2 is equal to sigma 3 is equal to 0. And they told us that the sigma ultimate in tension and compression, okay, is equal to 100 megapascals. Well, sigma 1 is less than sigma ultimate, therefore no failure. Everyone see that? Just the maximum stress is less than the ultimate tensile or compressive stress. What about something like this? Well, this is a little more tricky, all right? So now we're given a state of shear stress, and we need to figure out the equivalent normal stress. So what do? We say, okay, here is the state of stress where we are, right? This is a shear stress down here, and we know that it's centered at 0 because there's no sigma x, no sigma y. And then, so we can figure out what the radius is. What's the radius of this circle? The radius is 110 megapascals. So now we draw the circle, and sigma ultimate, we draw the goalposts here, and uh-oh, that's not good, right? You see that? We can find an equivalent state of stress at this location, which is outside the goalposts, and that will cause failure. So we say failure. And if we were to draw the sigma 1, sigma 2 box, all right, we have sigma ultimate here, ding, 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 right? And we could find that, this is sigma ultimate, comma, minus sigma ultimate, right? We can plot all these things, but where this corner is, but look, if we plot the equivalent state of stress, where we have sigma 1 equals the load, 110 megapascals, and sigma 2 equals negative 110, we're outside the box. We're out here. Okay, so that you can think of it that way as well. Okay, and then you can get mixed loading, right? Combined loading, something like this. So you have to do a little bit more work to draw the more circle. And when you do that, I'm going quickly because I'm running out of time. We can figure out what the radius is. This is a chance. This is when you want to use your Pythagorean theorem. Okay, when you're given mixed loading, you've got some sigmas and you've got some taus, and you've got really no choice but to figure that out. There you can figure out the radius, and you can figure out what the values for sigma 1 and sigma 2 are. Is either of these, so these are the principal stresses, either of these absolute value-wise larger than 100 megapascals? Just barely no. Okay, just barely no. So if you were to draw this on a sigma 1, sigma 2, right, you would be somewhere over here, and you're just barely not failing. Okay. Questions? Yes? What's that? In the middle one? How do I get 110? Oh, okay, so this is like someone hands you... Okay, good question. This is like you've done your analysis on a structure, and you look at a location, and you determine the state of stress. So these are handed to you in this case, right? So for whatever loading you have, right, this is the state of stress for this element and this defined orientation, right? These are givens, right? I'm handing them to you, right? I'm saying, look, this material is experiencing this state of stress, right? And then I have to go from that state of stress and figure out if the maximum normal stress, if any of the maximum normal stresses I can calculate is greater than the ultimate tensile or ultimate compressive strength of the material. Am I making sense? I think I'm not making sense somehow.
I don't know, but it just given how do you get 110?
Yeah, so the 110 is because I told you that's what the state of stress is. I'm telling you a couple things. You're told that the material has an ultimate compressive strength or ultimate tensile strength of 100 megapascals. That material will fail when the maximum normal stress is above that. You're also told now I go to a material system, and it's got a shear stress of 110 megapascals. Now I had to compare. This is like comparing apples and oranges. Right? I can't compare them because this is a shear stress and this is a tensile or a normal stress, right? So in order to compare them to each other, I use more circle, right? This one, it was comparing apples to apples because this is a normal stress and this is the yield stress, okay? We can talk about it after class if you want. And then this is also like comparing a mixed basket of apples and oranges to just an apple or an orange. And I got to come up with the equivalent apple from this mixed bag. Okay? All right? There's a question. Okay. Okay, maximum shear stress in 10 minutes. All right. So, Tresca is the name. Maximum shear stress is the game. All right. So, there's more to this than what we're saying here, but the basic idea is that shear stress dominates the failure, and you can actually see this. If I don't know if our LA was pointing it out, but when you do the tensile testing of the aluminum sample, you could actually see a couple of things. Sometimes the material would fail at 45 degrees. Often it would fail at 45 degrees. All right? Why? Because the equivalent shear stress, right? That's happening at 45 degrees. The maximum shear stress is 45 degrees relative to this axial stress that's being axial force, axial loading, axial stress that's being applied. You can see that here, right? It's 90 degrees of rotation on more circle. It's going to be 45 degrees of the element. And then there are these things called Luder lines, probably seen that wrong, that you can actually see form as you start to yield the material. Okay? So there are these at 45 degrees. So the maximum shear stress that we can have here, and we talked about this already, right? We did the whole thing. It's sigma 1 over 2 for tensile loading. And it's going to be happening at 45 degrees. So we can think about this shear, state of shear, and when you get to the maximum, absolute maximum shear stress or maximum in-plane shear stress, it doesn't mean that the normal stresses go to 0, right? That it can. There are situations where it can. This is a case, though, where when you're here, right? If it's pure shear, then it could, right? But in this case, right, we know that we get down here, and then the sigma x prime and the sigma y prime are also going to be equal to the tau max. Okay, for this particular case, you see that, right? Because the radius is the same as the distance from the origin in this particular case. So for uniaxial loading, we've established that the absolute maximum shear stress is going to be sigma y divided by 2. And we discussed this prior. So this is saying, okay, sigma 1 is this, sigma 2 is this, sigma 3 is equal to 0. And so we have again said, 45 degrees is where the magic happens. Okay, for in-plane stresses with sigma 1 and sigma 2 both having the same sign, all right, so if they both have the same sign, so like sigma 1 and sigma 2 are both positive, or sigma 1 and sigma 2 are both negative, okay, then you can say that the sigma 1 has to be less than or equal to sigma y, and sigma 2 has to be less than or equal to sigma y. If they have opposite signs, then it's the absolute value of the difference, okay, of these two has got to be less than the sigma y, or the sy. Okay. So here are some of the examples, right, where you have these tau maxes, absolute maxes that you're interested in making sure that your Mohr circles are in the bounds. Okay, and here's another case. So in this case, so we talked about field goals, all right, for maximum normal stress. Maximum shear stress, it's more like you're going down the highway, all right? I don't know, because field goal is vertical. This is more horizontal. I don't know, maybe the analogy is bad, but what you got to see is that your Moore circle needs to be inside this limit. Okay, that's going to be the criterion. And so you can see that we have a sigma 1 and a sigma 2 here for our plots, and so they behave. If you go through these different scenarios, what you'll see is that it does form these nice squarish boundaries when they have the same sign. And that's what we're saying here. Sigma 1 has to be less than or equal to sigma y. Sigma 2 has to be less than or equal to y. See? All that's true if these are the limits, if this is the sigma y. Okay? So sigma y, or negative sigma y, right? You see that? In quadrant 1 and 3, you just have to be in the box. Stay in the box. But in quadrants 2 and 4, when you have them with opposite signs, which is what you have here and here, it then has to satisfy this rule. And this rule, all right, if you think about it, you can, right, so this was just sigma 1 has to be less than or equal to sigma y, sigma 2 has to be less than or equal to sigma y. This, you have a relationship. And if you think of sigma 2, right, just imagine that there's no absolute value sign. Then you would have, and this is an equality instead of, it's an equal sign instead of a less than or equal sign, right? And then, rather than an inequality here, or greater than or less than, sorry. Then you could say that, okay, I move sigma 2 over to this side. I have sigma 1 minus sigma y is equal to sigma 2. All right, you see this? Sigma 1. If I had no, if sigma 1 and sigma 2 are greater than 0, then I can just write down sigma 1 and minus sigma 2 is, let's say, less than or equal to sigma y. Then I can write sigma 2 is greater than or equal to, well, let's do it this way. I'm just going to say this is equal right here because I just want to draw a line. Then I can say that sigma 2 is equal to sigma 1 minus sigma y. Okay? So this would be in quadrant, no, I just did it all wrong. They're opposite signs. If sigma 1 is greater than 0 and sigma 2 is less than 0. All right, so then then we can get rid of the absolute value sign. Okay, then we're sigma 1 greater than 0, sigma 2 less than 0. That puts us in this quadrant right here. What we end up having is a line. All right, that's what this line describes. So these plots end up having this kind of diamond-like shape at 45 degrees. And once again, if you're in the box, you're safe. If you go outside the box, you're going to fail. All right. So another example, once again, we can have different scenarios where we have 50 megapascals, and then we need to figure out, okay, how does this compare to sigma y? All right, so you can say, all right, we're using the maximum shear stress theory, but I can just compare sigma 1 and it's less than sigma y, so there's no failure here. We go back to this pure shear situation. This case, the allowable tau max is SY over 2. Remember that? We said sigma 1 divided by 2 is the absolute maximum shear stress. And the circle goes outside of that, right? Because the shear stress was told to be 110 megapascals. So this will definitely fail, right? According to this criteria. And if we were to draw it here, we would draw a point out in this region like this, okay? And then if we do one more example, okay, which is the same state of stress that we saw previously, we can figure out what the maximum shear stress is. This is going to be just outside, and so we're going to have failure. Okay. So I have to end. You have to go to Thanksgiving. I'll put up the this slide again for anyone who missed it in the middle or in the beginning. And I do hope that everyone has a very safe, happy Thanksgiving. And we'll come back on Tuesday to talk more about failure criteria. Right? And we've discussed 2 failure criteria already: maximum normal stress and maximum shear stress. All right? Thank you. Have a good one.